My wonderful students, have your clickers ready to go. We're going to do some clicking. And we're going to collect homework 7 in just a second. But before we do that, I have to give a shout out to the women's basketball team, also going to March Madness. And so, that's right. My opinion is Arizona State, maybe they should just go to the beach instead of showing up at the arena. I mean, forget about it. They're going to get crushed. All right. Homework 7. No big surprise. Last names O through R. Bring your homework up here. If you want to live. Good, just put it right here. Thank you. Yeah, you better move that out of the way. Last names O through R. Very good. Right over here. Okay, thank you. Great. Nice. Okay. Okay, great. Thank you. Good. All right. Oh, a hound dog. Very good. Thank you. Okay. Good. Okay. Whoa, you did it in ink. You did it in ink. It's nice. Good.
Like it?
Well, I don't know if I like it, but I am impressed that you would do it in ink.
Yeah, I always do it on a sheet of paper separate, and then I write it down.
Oh, okay.
Yeah.
That's good. All right, thank you. Last names O through R. Bring your homework down here. Move it. Let's go. Last name O through R. Don't make me come and get it. Right over here. Right over here. All right, thank you. Okay, everybody else, send it to the aisle, and aisle people, send it on down to the front. Get this stacked up here. Homework, homework, homework. What is this? Gosh. Seth Rung. Homework, please. Homework. Oh, lovely homework. Homework. Are you last name O through R? Yeah, okay, you're in there. Good. You're in my pile. You're in this pile, but not the main pile. Okay, man, thanks. Just slap it over there. Excellent. You guys got it? What are you guys fooling around with there? You got the homework? Come on. You're in the front row. You should be first above everybody. You guys are slacking up here. Gosh. I understand you did this in SI a couple weeks ago. You did this basic problem a couple weeks ago. For SI.
Oh, yeah, we did.
Yeah. Good. So they should have crushed this. Last name? In that file. Here come a couple more late birds. All right. What's your last name? What?
Hold on.
Oh, with the R? Yeah, you're in my pile. Put it on top of this middle folder. Put it on top of that. Yeah, don't forget your name there. You got your homework? Homework? What's your last name again? All right. Okay, let's get going. Just a short announcement about homework. Okay, the next homework is going to be after the exam. And I'll try to get these graded and back, my pile anyways, on Friday. So O through R, look for your homework from me on Friday. But the next written homework that we do, it's going to be a do-over type, homework, but it's going to be after the exam. So don't worry about anything. Between now and the exam, study your brains out for the exam. You don't have any written homework to worry about. And by the way, the answer for the escape speed, you can actually look it up on the internet. It's 11,000 meters per second approximately. Anybody remember getting that for an answer? 11,000 something? Yeah. So 1.1 times 10 to the 4. And what we were talking about in, let me pop this down. What we were talking about in All-Stars yesterday, we had a good bunch of people in there working on the problems, working on the homework together, kind of thrashing it all out at the marker board and stuff. And it was interesting to point out that the mass of the space shuttle actually cancels. That's the escape speed for escape velocity, they call it, for anything launched from sea level, basically. And it doesn't matter the mass of it. And that's because in the kinetic energy equation and in the potential energy equation, John, as we saw yesterday, the mass of the space shuttle is in both sides of the equation, so they cancel. But the mass of the Earth is not. It's only on the potential energy side. It's not on the kinetic energy side. So it works out kind of nice. Okay, let's get down to Chapter 9. We're going to dip into Chapter 10 today. And Exam 3 is going to cover as much Chapter 10 as we can cover on Friday. We're going to have some demonstrations on Friday too. So last time we talked about leverage, and hopefully you remember this diagram because we're going to calculate a lever arm, R perpendicular, with your eye clickers here in just a second. And the lever arm, R subscript perpendicular, is this right angle segment, or the right angle side of a right triangle, for which the line segment between the pivot and the point of application is the hypotenuse. And so it's given in this diagram here. Now, what we're going to do is calculate a lever arm on your iClicker. So let's go ahead and get your iClicker turned on. Frequency DD. All right. Cedeno, where are you at? No, Cedeno. No, not Mr. Cedeno. He's not here. Where are you? Oh, you're over there? Okay, good. All right. All right, here's your question. Calculate, so it's a wrench problem. Calculate the lever arm R perpendicular for this force, F equals 100 newtons. And the angle of tilt is 55 degrees below horizontal, as you can see. And the red dot, let me dim out the wrench. Okay, that dims it out a little bit. All right, so the pivot point is at the jaws of the wrench, the circle with the cross in it. And the red dot is out at the other end. That's where you're applying it. All right, so make a sketch and calculate. You have everything you need. And we'll go through the calculation in the end. So go ahead and talk with your neighbor. Coordinate. Talk with Kevin over there on the aisle if you get stumped. It's not a tricky calculation, but you have to know how to set it up. And it's kind of a new setup. So although you do have multiple choice here. So let me start the problem. My clicker went off. Okay, hold on a second here. Yeah, so make your sketch, talk with your neighbor, kind of see if your neighbor's got any tips, or maybe you can give some tips to your neighbor, which I see a lot of you doing. Kevin, that's what we want. Even if they can't talk to you, if they can talk to their neighbors, that's good. And I'll just give you a few minutes here to do it. Kevin, can you come here a minute? I just got a brainwave. You know what you could possibly do instead of roaming the aisles? Just go and sit down in the middle of the, start class sitting next to some, especially somebody like this, the guy with the Boston Red Sox hat. Nobody's sitting next to him, or anybody else like that. or anywhere really. And then, after a minute or so, if nobody asks you a question, go seat yourself somewhere over here on this side and so forth. And that'll maybe stimulate a little more interaction with you. All right?
Should I do that next week, or you want me to start sitting?
Do it now. You can leave your knapsack up here if you want. Just put it up here on the table, and that's fine. Yeah, just go make yourself at home in one of the, somewhere. No place in particular, just. Good. What's really interesting is just what's really interesting is to see all you guys pointing at the screen and pointing at your notebook as you talk with your neighbors. It's really good. Yes, Santi.
And where it makes a perpendicular with the line.
Oh, wait a minute. That's late. What's your last name? You're in my pile and you're late. All right, go back to your seat. Get your cooking done. Okay, one more minute. You don't really need the force to calculate this. Thirty seconds. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Raise your hand if you voted for 0.246. Sweet. Okay, good. That is that's your answer. Now, what we're going to do is double check the trig. So if you did not get that, and if I can see about 50 students did not get that, let's go through the trig. All right, so here's the original setup, and this is without the wrench drawn in. I removed that. And the distance from the pivot to the point of application, 0.30 meters. So that's 30 centimeters. Okay, and the tilt angle is 55 degrees below horizontal, angle theta. Now, what you got to do is draw a line from the blue line of action of the force. Somewhere along this line, let me get my cursor over here. Somewhere along this line here, you could draw a perpendicular line that goes straight through the pivot. All right, that's what you got to do. Now, if you're sketching this in your notebook, it might look a little shaky, but this one is right on the money. Right there. All right, it's from the line of action down here. It's perpendicular. In other words, 90 degrees. And it goes right through the pivot point. Now, that's your lever arm. The distance from the pivot point down to the point of application, that's your hypotenuse. All right? Question? To the line of force. Yeah, so yeah, I mean, if you put this one here, this vector here, down with its tail down here, then it'd be perpendicular. Carly. What's the what? F perpendicular? That would be the other way to work it out. The component of the force perpendicular. And then you use this as your R. So it's perpendicular. It's perpendicular to this line of force. All right? All right, so here's your triangle. Okay, in green. Let me just flip it out here. Okay. And here's the right angle. And there's the hypotenuse, our perpendicular, and the hypotenuse 0.30 meters. So now it's pretty easy. And this angle down here, I didn't mark it, but this is the 55-degree angle down here. So opposite and hypotenuse, that's the sine. So 0.30 meters times the sine of 55 is equal to r perpendicular. And that's your answer. All right? Now, the fact that we're going over this in lecture as a calculation might tell you about something that you might see on exam 3. Now, I'm not saying anything. I'm just saying. All right. Now, I want to talk about stability. We didn't quite get to this last time, and I want to kind of give you some visuals of stability. Now, here's a this is like a first grader's pencil, right? Really big, around, and short, the little fingers and stuff. And it's balanced on and notice that the free body diagram over here. Let me get my cursor. Free body diagram is balanced, so no great shakes about that. But the other thing is the weight force is at the center of gravity or the center of mass is going straight through the pivot point, which they're assuming is the center of the bottom of the pencil. And the normal force is acting at the center of the bottom of the pencil. All right, now that's going to change in a minute when we tip it a little bit to the left. All right, so this is stable configuration here. Everything's hunky-dory. This is figure 2 from chapter 9. Now, it says in chapter 9 that a system is said to be in stable equilibrium if, when displaced from equilibrium, in other words, tilted a little to the left here, it experiences a net force or a torque in a direction opposite to the direction of the displacement. So this one's tilted a little to the left. Does it experience a torque back the other way? If so, then it's a stable equilibrium. Well, let's take a look at it. Look at this. Your weight force is straight down from the center of mass as always. Right? That's the way it works when you do all the calculus. You can consider the forces as acting at one isolated point, the center of mass. But now the pivot point is over here at this corner of the pencil on the left. That's where if you tilt it this way, that's where the axis, the tilt axis is. All right, so now you can see that even though the free body diagram is balanced out, copacetic, they're not lined up. You know, the normal force acting through the pivot point, this corner, is a few centimeters to the left of the weight force. So you've got an uneven application of forces, and you're going to get a spin. All right, now what direction is this spin going to go? What do you think? To the right? My right or your right? Clockwise? Good answer. That's what you don't want to say right. You want to say clockwise or counterclockwise in this diagram. And the answer is yes. And this is a quote also from the caption of figure 3. The pencil is displayed slightly to the side, counterclockwise. Its weight produces a clockwise torque that returns the pencil to its equilibrium position. So that's this. Okay, so here's this kind of aqua colored arrow curved. That represents the torque clockwise about the pivot point. Question? Yeah, good point. For that, you have to do a bunch of calculus and stuff. And trig out the wazoo. So we're not going to analyze it in those terms, although we could. And some people are experts at calculus, but other people are not in this class. But there is a point, and we're going to do the unstable case here in just a second. Hey, so make a note to yourself, this is the stable. And really, what you're saying is that there's a range of displacements left and right for which which are stable. The displacements yield a back force or back torque back to stable equilibrium. But now there is a point, as Rachel was pointing out, where if you go past that point, now it's going to tip all the way over to the left. There's not enough torque. And I mean, if you think about it, if the center of mass gets to the left of this corner here, bye-bye, baby. So then it boils down to that. Now we're not, but we don't have any dimensions on the pencil here, the thickness, the height, or anything like that. So so we can't really calculate an angle, but I mean, if you did have the dimensions, yeah, a little trig out the wazoo, and you figure it out. Let's look at the next slide. There's unstable. See, the weight force here is now to the left of this pivot point. And now in this situation, you have an unstable equilibrium. Here's your torque. It's away from straight up and down stability. All right? So as you sensed, using your spider senses or whatever it was, your brain cells, there is a limit beyond which the torque will change direction, and then you'll be in a catastrophic failure. Your equilibrium will collapse. Your building will fall. So for those of you, well, hardly anybody here is going into engineering, although I think there's a few engineering majors in here. But I mean, if you're an engineering major, your building's going to fall over. The Leaning Tower of Pisa. It's, raise your hand if you've ever been to Pisa in Italy. Anybody? One? Wow, that's amazing. A lot of people. And when you were there in Italy, did you see the Leaning Tower of Pisa? It's really tilted. And it's, a friend of mine sent me a photo, because she knows I talk about the Leaning Tower of Pisa and Galileo all the time. And I thought to myself, oh my God, that thing really is really tilted. But it's not, and they've done things to stabilize it and stuff, but it's the Leaning Tower of Pisa is not at this point, at least not yet. So hopefully it will always remain where it is. Leaning Tower. So anyway, so that's what you got. So the system is unstable if, when displaced, it experiences a net force or torque in the same direction as the displacement. So what that means is your displacement gets bigger. The other one, the previous one, you have a displacement counterclockwise. Your torque is clockwise, so that's going to minimize your displacement. That's going to decrease your displacement, and you're going to go back to zero displacement straight up and down. This one, it's just going to keep getting bigger, all right? Now, the reason that, nobody's going around studying pencils and stuff like that. Not even Galileo studied that. But this confluence of ideas, equilibrium, two kinds of equilibrium, displacement, which has a direction and a magnitude, and that direction and magnitude affects the kind of equilibrium that you have. All of that's going to be critical as a set of concepts when we start studying oscillating systems. Like a good old, have you guys done springs in the lab yet? Springs? Okay. So springs, oscillating back and forth, the spring constants, stuff like that. All right. Now nobody goes around researching springs except for maybe the engineers for the company that makes springs. But otherwise, the springs were discovered a few hundred years ago, figured out. But they're an oscillating system. The oscillating systems that we do have active research in are ocean waves. It's interesting. Ocean waves transport energy and momentum across the ocean. If there's some storm off the coast of West Africa, we get waves over here in Florida at Cocoa Beach. But it's not that water's being pushed across the ocean, because it's the currents don't go that way. What's being propagated is energy and momentum in the form of wave energy and wave momentum, and that propagates, okay? And a disastrous or catastrophic case of wave propagation, of course, is a tsunami or, God forbid, a tidal wave from some mountain collapsing over there in the, where is it, the Azores, no, not the Azores, the Canary Islands. I think it's the Canary Islands. There's a volcano over there that they think it's unstable, and if the side of it collapses and falls into the ocean, they on Discovery Channel say that there's going to be a big 1,000-foot tidal wave that forms and greases Florida and everywhere on the east coast of the United States, faster than a jet plane. So hopefully that won't happen anytime soon. But I'm also skeptical about that claim. But the point is, that's an oscillating system, and we definitely want to know all about those babies. Electromagnetic radiation, that's also on the list here. Electrons and photons, those are oscillating systems in the quantum mechanical sense. So yeah, we definitely, even though we really don't care about pencils and springs too much, the principles that we learn with that. Here's another, for those of you that are pre-med types, here's an oscillating system, the human heart. And when the human heart stops oscillating in the normal manner, the regular sinus rhythm, pa-pump, pa-pump, pa-pump. When you get fibrillation or something like that, you got trouble. All right, so we want to know all about that bad boy and why it happens. And what keeps it in sinus rhythm. So all this stuff, yeah, pencils are nice, but yeah, cardiology, electrocardiology, definitely something we want to know about. All right, let's go into chapter 10, and guess what, guys? We just skipped over a bunch of chapter 9. I think we went from chapter 9.3 over to chapter 10. So we're but there's the last section of chapter 9. If you are a pre-med, you might want to read it and study it for your self-edification. But we're not going to dip into it. Question? I think that's what it is, 9.3. Wherever we, stability. We're skipping from the stability, from those diagrams of the pencils to chapter 10. All right. Although I think there's problems at the end of the chapter you could maybe, and I keep saying I'm going to promise you guys a list of problems that I like, but I'm going to do it. I this time for sure. All right, so, yeah, Sunday night. Oh, yeah, here it is, 11:30 Sunday night. Yeah, okay. No, I'll try to make it a little bit faster now. All right. Now, angular momentum and acceleration. Here's some stuff we already know. Omega, the angular rate of change, or the time rate of change of the angular coordinate theta. Delta theta over delta t. And we know that omega is equal to the linear or tangential speed at a given point divided by the radius to that point, right? Which is diagrammed here on this disk. And for that reason, V is also equal to omega r. Right? Now we're going to do a little bit of manipulation, Chelsea, with different equations and stuff here, formulas and stuff. So let's just hold on to our hats. All right. Now, tangential acceleration. When we were doing uniform circular motion, I said, all right, with uniform circular motion, that means the orbital speed, it's circular, and the orbital speed v is the same everywhere on the circle. But that doesn't have to be the case. For instance, you put a CD into your CD player inside of your vehicle, it spins it up from 0 to, whatever the RPM rate is of a CD player. Right? So there's a little bit of acceleration. And so the points along the edge of the CD, every dot on the CD has a different velocity, and it can change. So you can get a tangential acceleration. Now the tangential acceleration, A subscript t, is basically delta V over delta t if it is, if you're just doing the magnitudes here now. Delta V over delta t is directional as well. The centripetal part is not concerned with the magnitude, but only the direction. But if you're concerned about the magnitude, delta V over delta t, that's normal acceleration. But now V is r times omega, omega times r. So really the numerator of that fraction is delta of r omega. Now r, for any point located on that wheel, on that disk, r is fixed, so it doesn't change. And that means that the only thing that's changing is omega. If you're accelerating from 0 to 500 RPM, does anybody know how fast a CD spins? Anybody ever taken one apart? I'm gonna have to look that up. So whatever the RPM rate of the CD is, 0 to that RPM rate is an acceleration. So delta omega over delta t, that's your angular acceleration. And we use the symbol alpha for that. It looks like kind of a curvaceous A. It's a Greek lowercase alpha. All right, so the centripetal, or excuse me, the tangential acceleration is equal to r times alpha, the angular acceleration, which is delta omega over delta t. All right? Now, angular acceleration is therefore defined now. And we can set up a table of all the rotational analogues of, regular straight ahead motion, point A to point B motion, linear or translational motion. We can now do rotational analogues for that. So let's take a look at that. Here's a table. This is table 1 from chapter 10. And I just, did a screen grab of this. So your rotational coordinate is theta, an angular coordinate. The analog to the velocity is omega. V is delta x over delta t. Omega is delta theta over delta t. And then the analog to acceleration, acceleration A in F equals ma, that's delta V over delta t. That was like the first week of classes. All right. And the analog to that in rotational mechanics is alpha, and that's basically the tangential acceleration divided by r. So you can see theta is x over r, omega is v over r, and alpha is a subscript t over r, tangential acceleration. Right, so those are the analogs and the relationship between the three of them. Now this one over here, on the bottom right, the tangential acceleration related to the angular acceleration, Go ahead and put a circle around that or star, because what we're going to do, that tangential acceleration in the top of the denominator in this circled expression, that's the A of F equals ma. That's Newton's acceleration. So this is actually true. F equals ma can be converted into a slightly rotational format, mr alpha. All right? Because the tangential, I mean, if you look at that circled equation there, alpha equals at over r, just cross multiply the r, and you get acceleration at equals alpha r. All right, put that in for a, and you get mr alpha. Right? Now, no great shakes about that. That's just a little bit of algebra. Okay, so here it is at the top again. But now, let's think about that force. And, you know, the force can make a torque depending on where you apply it and in what direction you apply it. You can get counterclockwise or clockwise torque. You can get a little bit or a lot or not even any torque. Right? So if you do apply mr alpha, what's the torque that applies to that or that corresponds to that? Because remember, you know, on the pencil case, we had two different forces applying, but they didn't always provide a torque. They didn't always produce a torque. When they were face to face, toe to toe, no torque. But when they were offset by a few centimeters left or right, then you got some torques, either clockwise or counterclockwise. So the formula for torque, and let's just assume it's a circular path, therefore R is perpendicular to force, and R is going to be your lever arm. The torque is Rf. And that means that the torque is also mr squared times alpha. And that last equation, tau equals mr squared alpha, that is important. And we're now ready for some more rotational analogues. All right? The torque is mr squared alpha. Now here's what I want you to think about. Alpha is a dynamical quantity. It's measured with angular measurements and delta t, temporal measurements. M is in kilograms, so we measure that in a scale. And r squared is the square of a distance from the pivot, from the axis of rotation, out to the object with mass m. And so that's measurable with a meter stick or something. All right, so mr squared and alpha, those are all measurable things. And the property of the object is mr squared. Its dynamical condition is encoded in alpha. Right? So, another bit of rotational analogues. F equals ma, okay, Newton's second law. The rotational analog to that is the one we just had. Tau equals mr squared alpha. Now, the rotational analog of the inertial mass. M in F equals ma is the inertial mass. And therefore, the rotational analog of that is mr squared. And that, my wonderful students, is called the moment of inertia. On Friday, I'm going to bring in a big bicycle wheel, and we're going to do some demonstrations of angular momentum and moment of inertia. And hopefully I'll have some homework to hand back and some scores to do. But, okay, I was going to give everybody a bonus point. Clicker, see, everybody turned around up there. See, no, I'm not going to do that. But we're at the end. We're going to do angular momentum and the ice skater effect next time. So see you then. Read more of chapter 10. Read as much as you can. You're dismissed. Boy, I had those guys juked up there.